All right, so this is the aspirin part 2. Okay, looks like I might need aspirin after this lesson. All right, so we're designing our aspirin lab from scratch, and we're using the Target 325. So we did this already once, but I want to revisit this again because we're going to go a little farther today, and a few people got lost in the sauce here. Okay, before we even redesign or start going through my redesign, I want to talk about what this lab is about. It's a back titration, just like we did for the Tums lab. And so I'm kind of hoping you understand what you did in the Tums lab that's going to help you do this lab. Now this lab's a little bit different because Tums, of course, was a weak base, and we overshot the equivalence point by adding extra acid. Here we have a weak acid, and we're going to add a strong base. We're going to overshoot the equivalence point. And the reason for back titration is because when we have a tablet that doesn't dissolve, okay, it's really, really helpful to add more than what's necessary to react with it, especially when it's mixed with other components. Okay, it's hiding there. And of course, we need to do hydrolysis or hydrolyze the acetyl group, okay, in the aspirin to make this react. So all of those things lead us to do a back titration, overshoot the equivalence point. Now, the target, of course, is 325. We'll get to that again. So we're going to go through those same calculations and go a little farther today. But before I do that, okay, my period 1, if you're watching, this is for you. Okay, we're period 2 today. Okay, what we want to do is the following. We want to add enough hydroxides to overshoot the equivalence point. Now, theoretically, we don't know where that equivalence point is, but because we're designing it around 325, we definitely have a value that's going to give us a place to start. And we know that it's going to be close to that, so that's there. But I'm going to draw this big arrow down. Okay, this is where I'm trying to help my other class, because I think this is going to be more helpful now that I think about it. So we're going to shoot past the equivalence point. Now, what is that equivalence point? Now, the whole purpose of the lab, okay, is to find this arrow. And this would be the moles of H plus that we're titrating that came from the what? Aspirin. What we're trying to do in this back titration is find exactly how much protons from the aspirin, which is a weak acid, that was neutralized. Once we have that, okay, because it takes 2 hydroxides, okay, we know we can do something with the stoichiometry. So once I know how much, I guess the real answer is how much hydroxide is needed to neutralize my acid, okay, then because I have 2 of them, I'm going to do some stoichiometry to get how many moles of aspirin, and then convert to grams and then milligrams, divide by 2 because we're crushing 2 tablets. That should be clear. Okay. Now, this line is unknown. That's unknown. And sometimes drawing it, it confuses people. Okay? But we get this line using this target amount. Okay, now, let me talk about this. We're going to add excess hydroxide to our crushed tablets that are being dissolved in ethanol. We talked about this. We're going to drop the excess base. We're going to stir and we're going to heat for about 15 minutes to allow, okay, the hydrolysis of the acetyl group. Okay, great. Then we're going to add because this is hydroxide, we're going to add protons to neutralize the excess base. Right? So let's find a new color. Okay? And so this is what we're going to back titrate with. And we're going to back titrate with hydrochloric acid. And we're going to figure out and carefully titrate with our pH probes exactly how much acid, hydrochloric acid, was needed to titrate the excess hydroxides. Everyone follow me? Good. Now, how did you solve, or how would we solve for this lab? Well, once I know exactly how much hydrochloric acid was needed to get to the equivalence point of the excess hydroxides, the moles of H plus equal the moles of hydroxide excess, correct? So the moles of HCl would equal the moles of the excess hydroxides. How do we get this arrow? We subtract the excess moles of hydroxide from the total. I can't say enough today, but you have to understand, once we know the moles of HCl, we know exactly the moles of excess hydroxide. We subtract that by the total red line here, and that's going to give us the moles of what? Hydroxide needed to exactly neutralize all the aspirin. Do my stoichiometry, and now we know moles of aspirin. Convert to grams, milligrams, divide by 2, boom, we're done. Some party people, okay, and Pablo, spreading the wealth. We need to know the total moles of hydroxide, correct? When we do this, we subtract, correct? And what we get is this arrow of moles that really represents the aspirin, okay? Now, it seemed to me that there was a misunderstanding in my first period because this is exactly what we did the Tums lab. Now, here's the problem that we're gonna run into today. We're gonna drop a strong base, correct? Because it's a strong base, it reacts with the CO2 in the air and the water in the air. It's deliquescent, very reactive. For me to figure out the total moles of hydroxide, I'm going to use a value that's estimated based upon starting amount of milligrams as my target. This arrow down is going to be adjusted. It was adjusted in your form last night. It's adjusted here. Okay, let me explain. This is what we did yesterday. Okay, we said, okay, if the target amount of aspirin is 325, we're going to crush 2 tablets. And that got us 650 milligrams or 0.60 grams of aspirin. The molecular mass was 180.185. grams per 1 mole. We know that the hydrolysis of the acetyl group is going to render 2 acid molecules that came from the aspirin that need to be neutralized. So, we know that for every 1 aspirin, 2 hydroxides are going to be needed. And this gives me what value from yesterday?
Moles of hydroxide.
Yeah, moles of hydroxide. So let's go red here. Well, it's going to give me the moles of hydroxide related to that. Let's not go red yet, but what's the value that we got yesterday? I mean, I'll do it again.
0.00722.
Yep, 0.00722 moles of hydroxide. That's what we got. That's not any arrow. Theoretically, it's this arrow because we're using that as a projection, as a guide to be around. We have to have wiggle room. Okay. So yesterday I drew an arrow down first. I think that's my confusion with some of my first period class. That would be exactly the moles of hydroxide needed to neutralize the aspirin if the tablets were 325. We don't know. This is a quality control test. We don't know if they're under, above, or at that, so we can't just stop there. We're going to have to add excess because what if there's more? but we need excess regardless because the design of the lab requires us to force, by Le Chatelier's principle, this forward. And as I said, it's a tablet. It doesn't dissolve. Having more of the solution of the base will dissolve it, okay? So this is not the excess. So we said to ourselves, what arbitrary value should we use? And yesterday I said, we're gonna add 0.01 moles of base excess. Why did I pick that? Because that's a safe number. I didn't want us working with 5 molar, so I didn't choose that. So this is an arbitrary value. 0.010 moles of hydroxide is my excess. You with me? I decided that just so that we're making this solution, it was a safe concentration. Hydroxide concentrations that go high get very basic and get dangerous. And then we added this together. And what did we get? This is important. We got a projected total amount of hydroxide moles. It was 0.01722 moles of hydroxide. Is everybody with me? Good. I added a projected excess. This is a back titration. We're gonna titrate the excess. I need the excess by Le Chatelier's principle to derive this to completion, to find every piece of aspirin in my tablet. So we crush it, we add excess, that's why back titrations are used. Is everybody with me with this number?
Oh, so that's the moles of OH in the aspirin plus extra?
Plus the excess.
Okay.
This is an important number. Stop for a second. To solve for the amount of active ingredient, or aspirin, when we get to it, once I titrate the excess and know the moles of H+, isn't that the moles of hydroxide? That's excess? I need to take that amount and subtract it by this amount to get whatever the moles of H+, the aspirin. Does that make sense? I need this number. I need to know this number. Just like your Tums lab. Except in Tums lab, we added H+. We back titrated with hydroxides. Hydroxide moles equal the extra H+. We subtracted from that number, and we got whatever this number was. We went backwards. In this case, divided by 2 times by 180, and we get the tablets. This is an important number. Does everyone agree? Good. Now, here's the thing that confused some people. That is a dynamic number. It's going to change. It's not the exact number. In our Tums lab, we got that number and we were done. It's not the case here. This is where people got confused. So pay attention. Okay? This number is not the actual number. It's a guide. Okay? Just stay with me. How do we calculate, okay, the molarity of the base? We said, okay, using this as a guide, I want to deliver this amount of moles. So I want to make a solution. Molarity is moles. So I want to deliver 0.01722 moles of hydroxide. And because we're making 100 milliliters, everyone's making their own solution, the most I can make is 100 milliliters. I shouldn't design this for 100 milliliters because I have to do what with a strong base? I have to standardize it. I have to use part of it. So yesterday I said, we're gonna make 100 milliliters of a solution. We're gonna use 20 milliliters of it to standardize. Probably just need 12 or 13, okay, but we're gonna use part of it. So we made a molarity. I wanna drop that many moles, okay, as my guide right now, and I wanna use how much? If I'm gonna use 20 out of the 100, how much do I have left?
80.
80. So let's go find this molarity. What did we get yesterday? 80 milliliters is 20 milliliters. So what we get, this was yesterday?
0.215.
0.215, right, that makes sense. So we got 0.215 molarity of the what? NaOH. Everybody with me so far? So we're gonna make 100 milliliters of a solution, and we're gonna pour off 80, measure that very, very carefully, and pour that 80 milliliters of that molar solution into our beaker with our 2 tabs, and that will always shoot the endpoint, theoretically, to this value. You with me? Good. Now, how do we come up with how much we have to make the solution? Well, I want to make 0.215 molar in a 100 milliliter flask. So I got to figure out how many moles it takes. So the molarity is 0.215. We're going to solve for the moles of the hydroxide we need. And we're going to make this in how much? Yes, so 0.100 liter. What we get for moles here? 0.002 or 0.0, what do we get?
0.02.
0.02 what?
15.
15
Also.
moles of hydroxide. And then we convert it to grams, right? Because you went to the molecular mass part, yes?
Wait, sorry, I'm just not following. So we were at 80.08 liters, and now we're at.
Yes,
what?
very
Do
good.
we add 20 back?
Nope. I designed the molarity I need around exactly how much I want to pour into the 2 tablets. Okay? That's how I designed that.
Okay.
And the reason I said 80 is because I think it's a good bet. We can easily measure 80, and we can still use 20 to standardize. So I said, what would be the molarity I need to pour 80 milliliters of this target moles? And it gave me that. Now, if I want to make this solution, I'm going to start with a 100 milliliter volumetric flask. I'm going to make 100, I don't have 80 milliliters. Besides, that wouldn't be smart. If I design this around 100 milliliters to make this number of moles, I'll pour that out and have nothing to standardize. I've got to take part of the base that I make and standardize. So what we did, arbitrarily decided, let's use 80 of the solution I'm going to make to deliver those moles. Therefore, I'll need that concentration to do that. That's how you use, that's how these formulas are actually used. We're in the nuts and bolts of chemistry. I can give you molarity as moles over liters, but until you go through this design, you see how you use it. Now, knowing that I needed 80 to deliver these moles, and that's my concentration, doesn't it make sense I need more moles to make 100 milliliters? And that's why it's a little bit bigger.
So,
0.0215 is bigger than 0.07 because I'm going to make 100 milliliters of it.
so now when you do the back titration, do you subtract from
We're
that
not,
number?
no, don't go to back, we're not right now anywhere near the back titration yet.
Okay.
Just stay with me. Now, what did we do yesterday? We took this 0.0215 moles of NaOH, and we're going to put a mole here, and we have what? Grams. It's 40 grams per mole, and you guys got 0. What? 0.86 grams of NaOH. And tomorrow, you're going to carefully measure out exactly 0.86. You're going to have to crush the tablets and use pieces of it and spend the time to make that. Now, what do you do with that? You're going to add it to a 100 milliliter volumetric flask. Make sure you get all out, wash bottle. And then you're going to dilute to the 100 milliliter mark. Well, actually, you're going to add some, get all the solids in, use the wash bottle, make sure all the solids are in here. Add distilled water, pre-dissolve it, and dilute to the 100 milliliter mark. That many moles diluted to what? 0.1 zilliliter gives you that molarity. We need that molarity because 80 milliliters of it will deliver those moles. Okay? We can do MV, moles over liter, questions all day, but until you start designing and playing with it, you see how this is actually used. And that gives me what? Extra milliliters to standardize because strong bases what? Strong bases are highly reactive. You with me so far?
Yeah.
Good. Now, let's take it a step further today. let's figure out the KHP standardization, because I really have to know what this concentration is. So, we gave ourselves 20 milliliters to play with, but I would design the titration for KHP to be 20 milliliters, correct? I'm gonna say 10. This is an arbitrary value. So I wanna put, of the 20, maybe 15 in my burette. The other 5, I'm gonna rinse the burette. Why would I rinse the burette with a titrant before that? We haven't talked about it, now's a good time. Why would I rinse the burette with the titrant? What if I rinsed it with water first and then put the titrant? Why would that be a problem?
Polarity would change.
It would change in what way? It would go up or
It
down.
would go up. No, down.
Yeah, you're diluting it. If I'm gonna put water in through that, there's water drips and drabs, and now I add the titrant, it's getting diluted. So you always rinse the burette with the titrant, and you have extra to do that. So maybe I'll add 5 to rinse, and I'll add 15. I'm gonna design this around 10. So, how do we solve for the KHP? Well, I'll do this. We want 10 milliliters. We want to drop 0.010 of the base. The base is projected to be what? 0.215 molar. So how many moles of hydroxide, theoretically, would I add if I drop 10 milliliters of that solution? And that's just 0.01 times 0.215, even I can do this math, is 0.00215 moles, correct? Moles of hydroxide. Why am I picking 10 milliliters? Because we have an extra of 20. I could pick 5, but I'm gonna pick 10. This is a standardization, yes. If I'm dropping, sorry, I just got those kind of used. They're up here. They bounce all over. All right. So any case, so we are arbitrarily designing this to be 10 milliliters. It's going to be more, but a little bit more. Now, I got the moles of hydroxide. Wouldn't that equal the moles of KHP? KHP is a monoacidic acid. So this would equal 0.00215 moles of KHP. Why do we use KHP? It's a weak acid. It's a solid. I don't have the drips and drabs of liquids. And it doesn't react. And it's got a big molecular mass. So what I gotta do is convert 0.0025 moles of KHP to grams. Let's do that. 0.00215 moles of KHP. That's, by the way, it's potassium hydrogen phthalate. Everyone says KHP. And 1 mole is how many grams? It's 202.44. What was the KHP? It's 204.22. Okay. Okay. My short-term memory's gone at this height. 20422. Okay. So what do we get for grams? What is 0.00215?
0.439.
Time, we'll do it 2. I got 0.439, is what you got?
Yep.
Okay, so when I solve for this, I get 0.439. And that's what? Grams of KHP. What's beautiful about KHP is I'm gonna measure that exact amount on a weighing dish. Spend the time. Carefully pour it into water. Do I care how much water? I don't care how much water. Will it dissolve? It's got a group 1 ion. So I'm gonna not worry about liquids. And that's gonna be what? My analyte. And then my burette, I'm gonna add, I don't know, 15 out of the 20 extra. It might be all right. I'm gonna add phenolphthalein. It'll stay clear in the KHP, the acidic solution. And we're gonna titrate to an endpoint using the indicator, like you've done, very carefully. And when the color persists for 30 seconds, I'm gonna measure, I'm gonna break that, I know it, okay? This is gonna go down, here's my initial volume, here's my V final. I'm gonna subtract that once this color persists. How do we solve for the actual molarity? Ooh, molarity is equal to what? Well, how much base did I add? And we decided that 10 would be projected, but we all know it's gonna be greater or less.
Greater.
Greater, just like our last lab. Why? Because sodium hydroxide is deliquescent. It's gonna absorb water out of the air, and it's gonna react with CO3. When it reacts with the CO2 out of the air, which is a Lewis acid, it becomes sodium carbonate. Because it's so reactive, it's constantly reacting, so this right here, my friends, is not the molarity. It's close to that. So when I solve for it, let's just come up with a fake number. Play with me right now. Let's make this equal to 0.01. Instead of being, that'll be, let's say, 0.8. So isn't that really 10.8 milliliters? Can we all see we're gonna have to add more base because it's more dilute than we expected, just like the last lab? Okay. Now, the cool part is, don't we know exactly the moles of base we just delivered? Because it matches the KHP. So we neutralize the KHP at this exact moles, so that's the moles. 0.00215. Now I'm making up this number here. Let's go find the new molarity. It's going to be under. So 0.00215 divided by 0.0108. Okay. So this is a fake number. Okay. So I get let's do 119. 0.119. 0.199 is the new molarity. On this example, you didn't do this yet. What did we project it to be? 0.215. What did we find? It was actually less. You're gonna find that. It's reacting in the air. That's why we have to standardize. Everybody with me so far? This is the part where the class before you guys got lost. Now that you guys know the new molarity, just like last night's form, you drop base on ibuprofen. Ibuprofen was an acid. You projected how much base, but then you had to standardize and correct. Watch. Once I know the exact molarity, what changes? Total moles stuff. Let's remind, don't I need this?
Yeah.
When I do the back titration and find the moles of H+, that's the moles of hydroxide, I've got to separate it from this to find the aspirin equivalent hydroxide used to neutralize it. I need to know this. How did we find this? I added an extra, and from this, I got what? This. My friends in chemistry, we added 80 milliliters, not of this, but of this. What does this line have to do? Go down or go up? I need to know this. This line is going what? We got this molarity by coming up with this value. This molarity, we said we added 80 milliliters of this to get here, correct? We did add 80 milliliters, but we added it of this, something lower. So I gotta take my molarity of my actual solution, this is fake, how much did we add? 0.08. I'm just gonna come up with this number. Let's go find the actual total now. We have to adjust it. 0.199 times 0.080. Okay. In this example, this is gonna change to 0.0159. It got less. Because we were assuming it was that concentration and it was less. This line now is actually what? A little bit smaller. And it's a number I desperately need. How we doing? Did I lose you? Good, because I lost everybody else in the first period. But knowing that information, I changed the way I presented this that way. Now, for those that I did lose, you don't want to mention something, how do we solve for the tablets? I need to back titrate with HCl, correct? That's the same, H plus is equal hydroxide, so the moles of HCl I need to back titrate the excess is equal to the excess hydroxides. I've got to take that mole and subtract, not by this overestimated number, by the actual number to get how much was needed, and I go backwards. So just like last night, we have to adjust this line going down. Yes?
Is there already like a fixed amount of moles of H plus in the beaker?
We didn't add any H plus yet.
Okay.
We've only been up to designing it around 325 milligrams.
No, like
We
the
came up-
purple line.
what's
is-
that?
The purple line is already there.
Oh, the purple line is there, we don't know what it is. I don't know how much back that I have to go to find the amount of hydroxide that neutralized my aspirin.
Okay, but all these numbers have been dealing with the red line.
Yes.
Okay.
That is an unknown, because what if my tablet has a lot of excess? Then the tablet has less aspirin. Okay, so this is a wiggle room thing here. So this is something we don't know. I can't say enough. So, everybody with me? Good, and that's what you did last night. You had to adjust that line down. Maybe that helps. Okay, now, how much HCl do we need? Well, what was the excess? 0.01. Is that truthfully the excess anymore?
No.
No, it's not. But you know what? I don't care, because since I have wiggle room, because I don't know what it is, I'm still gonna use it. I could subtract this new value. I'm sorry, I could add this, and I can find the excess, but I don't have to. It's gonna be close enough. So let's go design the molarity of the acid, and we'll finish up here. Remember, I know it's the target 0.01 is not true anymore. But because we're gonna find it, it doesn't matter if I'm off, okay? So, what do I do here? Okay, the target is 0.01, I'm gonna make a solution. Oh, we're titrating back, aren't we? So we've got the beaker filled with excess acid, correct? I'm sorry, excess base. And now we're gonna add what? Acid to neutralize the excess. So I can subtract it by my new number to get this hidden value. Okay, here's an arbitrary value. How much do you want to put in your burette? How much do you want to, what's the neutral? We did 20 milliliters last time. How much do you want to add till you get to the neutralization point? I'm gonna say 20 milliliters. Okay. The target is 0.01. I know this target has changed, but I don't care. It's still gonna work. Because if I need more, I have more. If I need less, I have less. Does that make sense? I'm gonna put 0.01 here. That's about what the excess is. It's not any more, but it doesn't matter. If we need more, we use more. So what's 0.01 moles over 0.02?
5.
Yeah, I wanna make that. And how much do I expect to use to neutralize my beaker of aspirin? 20. Okay, now, we're gonna make it from a 3 molar stock solution. How much of it do I need? Oh, how much are we making? How much you guys have another 100 milliliter flask. So you're gonna make 100 milliliters. And what's the molarity you need? And beast mode, what is this?
MV10.
Yeah, you like this one. So someone solve for that? 0.5 times 100 is 50. 50 divided by 3 is 12 point, no. So what we got? What's that value? Okay, I'll do it. I'll get it wrong on the video, people will like slam me. 0.5 times 100 divided by 3. 16.7. What does that mean, party people? I'm gonna measure out 16.7. I'm gonna put that carefully into a volumetric flask. Now your 100 milliliter, this is a 500. I'm gonna rinse out the beaker, get all the drips and drabs, and then I'm gonna dilute to the 100 milliliter mark. I'm not gonna use all of it, okay? I'll fill the beer up to 50 or something, and I'll have excess here because I just don't have any small enough of that. And that's the design, okay? But the biggest thing I want you to get from that, this arrow down is gonna change once we standardize. We set it up based upon the non-standard. Other class did not get that, hope you guys got that. Tonight's homework, there's nothing but complete your what? Procedure, okay? Yes. Oh, for this lab. The other lab is due Friday, if you have to keep working. There's no worksheets or anything else, no videos and checkbox quizzes or tonight. Yes?
When we standardized it, we got the value of the moles of NOH without its like reaction to other gases in the environment.
Yeah, we got to the first arrow by assuming that what we make is what's gonna be, but we know it's not. So but we badly need this number.
So is that value like the 0.0159 after it reacts, so it's smaller because?
Yes,
Okay.
yes, and that's the one we have to use. Yeah.
The 0.01, we could have changed that.
Yes, we could have figured that out and maybe made a better one here, but it's not gonna matter because if you need more, you use less. Right, it's a good point. You got it. Tomorrow we're gonna do it.